Dear student, I am Dr. A.K. Jain, Professor and Head Applied Science Department, James Engineering Management Technical Campus, Greater Noida. Today we shall discuss the second lecture of laser, in which we have to study the following topics: Einstein's A and B coefficients, relationship between A and B coefficients, conditions necessary to achieve laser action. In the last lecture of laser, we have discussed about the three important transitions, which are: number one, induced or stimulated absorption process; second is spontaneous emission process; and third one is induced or stimulated emission process. So these three important transitions, the relationship between them is given by Einstein in terms of A and B coefficients. So what are the Einstein's A and B coefficients? It has been shown here. The Einstein A coefficients are related to the rate of spontaneous emission of light, that is the second transition which we have discussed in the last lecture, and the Einstein B coefficients are related to the absorption and stimulated emission of light or radiation, that is first and third transition, which we have discussed in the last lecture. Let us consider that N1 is the number of atoms in energy state first, or you can say lower energy state, and N2 is the number of atoms in higher energy state 2, respectively, at any instant of time. So first of all, we shall discuss induced absorption. The transition we have already discussed. In this case, if the number of atoms in state 1 absorb a photon and gives rise to absorption per unit time, the probability of this absorption transition from lower energy state 1 to the higher energy state 2 is directly proportional to number of atoms in the lower energy state, that is N1, and the energy density rho nu of incident radiation of frequency nu. What is rho nu? Rho nu is the energy density of radiation incident on the atom in lower energy state. Then the probability is proportional to N1 and energy density of rho nu. So the probability, that is P12, is defined. The probability for induced absorption, that is equal to B12 N1 rho nu. What is B12? B12 is the proportionality constant, which depends upon the properties of lower energy state and upper energy state, that is excited state 2, and this constant of proportionality B12 is called Einstein's coefficient for absorption of radiation. Since this transition takes place from lower energy state to upper energy state, that is, it is also denoted by arrow, upward arrow. The direction of this transition is from lower energy state to higher energy state, or that is in the upward direction. Therefore, it is shown by upward arrow direction. This is equation number 1. Next, spontaneous emission, which we have also already shown in my last lecture. The probability of spontaneous emission transition from upper state 2 to the lower energy state 1 depends only on the properties of states 1 and 2 and the number of atoms in excited states and 2, and therefore the probability is proportional to N2 only. It does not depend upon the energy density of radiation, because this transition takes place automatically. There is no need of any energy density of radiation to initiate this process. This spontaneous emission transition takes place automatically. So therefore, the probability of this transition depends only the number of atoms in excited states, that is N2. So P21, that is spontaneous probability, is equal to A21 N2, where A21 is called Einstein's coefficient of spontaneous emission of radiation, which is constant of proportionality. And since this transition takes place from upper state to lower state, that means it is downward transition. So it is represented by equation number 2. Third important transition is stimulated or induced emission transition. This transition also takes place from upper state to lower in state, and therefore the probability of stimulated emission depends on the energy density of radiation rho nu of incident radiation and the number of atoms in the excited state, that is N2, as well as on the properties of state 1 and 2. This transition takes place only in the presence of external radiation. Therefore, this transition depends upon the number of atoms in excited state, and also it depends on the energy density of incident radiation. Since this transition takes place from upper state to lower state, so this is the downward transition. Therefore, the probability of this transition is directly proportional to the number of atoms in upper energy state, that is N2, and the energy density of radiation, that is rho nu. Again, this transition is also downward transition, which is represented by equation number 3, and the proportionality constant B21 is called Einstein coefficient of stimulated emission of radiation. Therefore, the total probability of emission of radiation from state 2 to state 1 is given by P21. That means total probability will be equal to the equation 2 plus equation 3, because both equations are the downward transition representation. Means spontaneous emission takes place from upper state to lower state. Stimulated emission is also takes place from upper state to lower energy states. Therefore, both transitions are downward transitions. So their downward transition means emission process. Therefore, the total probability will be the sum of equation 2 and 3. So therefore, P21 is equal to A21 N2 plus B21 N2 rho nu. This is the total probability of emission of radiation from state 2 to state 1, that is represented by equation number 4. Now, in thermal equilibrium at temperature T, the number of upward transition means absorption process, are equal to number of downward transition. Downward transition means emission process. Thus, from equation 1 and equation 4, we can write for equilibrium that P12, that is upward transition, that is also the absorption transition, is equal to P21, that is the downward transition or emission process. So P12 is equal to P21. So therefore, from equation number 1, you know that P12 is equal to N1 B12 rho nu is equal to P21, that is from equation number 4, that is N2 is common. So we have taken N2 out of this bracket. So A21 plus B21 rho nu bracket close, or we simplify this equation and we have the rho nu, that is energy density of radiation, is equal to A21 over B21 divided by N1 over N2 B12 over B21 minus 1. This is equation number 5. We have rearranged this equation in the form of equation number 5. That is very simple. You can do it very easily. Now, according to Boltzmann distribution law, the number of atoms N1 and number of atoms N2 in energy states E1 and E2 in thermal equilibrium at temperature T are given by N1 is equal to N0 e to the power minus E1 kBT. This is equation number 6. And N2 is equal to N0 e to the power minus E2 over kBT T. This is equation number 7. Where N0 is the total number of atoms present in the ground state and Kb is the Boltzmann constant. You already know about this constant. So Kb is the Boltzmann constant and its value is 1.38 into 10 to the power minus 23 joule per Kelvin. Dividing equation 6 by equation 7, we have N1 over N2, that is e to the power E2 minus E1 over kBT, or E2 minus E1 is nothing but it is the energy difference between the two energy level, that is given by h nu. So E2 minus E1 can be replaced by h nu. So therefore N1 over N2 is equal to e to the power h nu over kBT. This is equation number 8. Putting this value of equation 8 in equation number 5. So we have the energy or density of radiation, that is rho nu is equal to A21 over B21 divided by N1 over N2 B12 B21 minus 1, that is just replacing N1 over N2 by equation number 8. So this is rho nu, that is A21 over B21 divided by B12 over B21 e to the power h nu over kBT minus 1. This is equation number 9. Now we compare this equation number 9, that is energy density of radiation, with the Planck's radiation formula, which gives the energy density of radiation. What is Planck's radiation formula? Planck's radiation formula is the energy density of radiation rho nu is equal to 8 pi h nu cube over c cube into 1 over e to the power h nu over kBT minus 1. This is equation number 10. When we compare equation number 10 with equation number 9, we see that B12 over B21 over B21 is equal to 1. You can compare this equation with equation number 9. Also that B12 is equal to B21. This is equation number 11. Similarly, if we compare the denominator, then we can see that A21 over B21 is equal to 8 pi h nu cube over c cube. Hence, this A21 over B21 is equal to 8 pi h nu cube over c cube. Similarly, B12 over B21 is equal to, that is 1. So this is equation number 11, that is B12 is equal to B21 and A21 over B21 is equal to 8 pi h nu cube over c cube. This is equation number 12. So equation 11 and equation 12 are called Einstein's relation of A and B coefficient. Equation number 11, that is B12 is equal to B21, means that probability of stimulated emission, that is B21, is same as that of induced absorption, that is B12. This means that if these two processes will occur at equal rates, so that number of no population inversion can be attained in a two-level system. Second is the ratio of spontaneous emission and stimulated emission is proportional to nu cube, because all other factors in equation 12 are constant. So A21 over B21 is proportional to nu cube. This implies that the probability of spontaneous emission dominates over induced emission more and more as the energy difference between the two states increases. Conditions for necessary to achieve laser action we have already discussed, so you can study. These are the three important conditions. Following are the conditions necessary to achieve laser action. Number 1, there must be population inversion. What is population inversion? An assembly of atoms in which the majority are in excited state. This is the fundamental principle involved in the operation of laser. Second is the excited states must be metastable states. Metastable states are those states or those excited states whose lifetime must be 10 to the power minus 3 seconds or more instead of the usual excited state lifetime, that is 10 to the power minus 8 seconds. So these excited states whose lifetime is 10 to the power minus 3 seconds or more are called metastable states. Third important condition is that the use of pair of reflecting mirrors as resonator at the ends of the system. System means active medium consisting of collection of atoms, molecules or ions in solid, liquid or gaseous form, so that emitted photons must be confined within the system long enough to allow them to stimulate further emission from other excited atoms. One of the mirrors is made fully reflecting, that is fully silver, while the other is partially reflecting, that is partially silver, so that an intense laser beam can emerge out of this partially reflecting mirror. So the three important conditions necessary to achieve the laser action is that number 1, there must be population inversion. Second one is the excited states must be metastable states, and third is we have to use the pair of reflecting mirrors as resonator. One of the mirror is fully silver and another mirror is slightly partially silvered as compared to fully silvered mirror, so that intense laser can be emerge out from the partially silvered end of the system. Thank you. Following are the conditions necessary to achieve laser action. Number 1, there must be population inversion. What is population inversion? An assembly of atoms in which the majority are in excited state. This is the fundamental principle involved in the operation of laser. Second is the excited states must be metastable states. Metastable states are those states or those excited states whose lifetime must be 10 to the power minus 3 seconds or more instead of the usual excited state lifetime, that is 10 to the power minus 8 seconds. So these excited states whose lifetime is 10 to the power minus 3 seconds or more are called metastable states. Third important condition is that the use of pair of reflecting mirrors as resonator at the ends of the system. System means active medium consisting of collection of atoms, molecules or ions in solid, liquid or gaseous form, so that emitted photons must be confined within the system long enough to allow them to stimulate further emission from other excited atoms. One of the mirrors is made fully reflecting, that is fully silver, while the other is partially reflecting, that is partially silver, so that an intense laser beam can emerge out of this partially reflecting mirror. So the three important conditions necessary to achieve the laser action is that number one, there must be population inversion. Second one is the excited states must be metastable states, and third is we have to use the pair of reflecting mirrors as resonator. One of the mirror is fully silver and another mirror is slightly partially silvered as compared to fully silvered mirror, so that intense laser can be emerge out from the partially silvered end of the system. Thank you.